let's talk about continuing on in chapter 6, looking at trusses, looking at structural analysis. Let's talk now about method of joints. So not joints, sections. We just talked about method of joints. I was about to say, we just talked about method of joints. So now we're going to talk about the other method, the method of sections. Method of sections basically operates on this principle. It's the idea that we can cut a truss into multiple pieces. And draw free body diagrams of the smaller pieces. And anything we can draw a free body diagram of course, we can apply equilibrium equations. And just like normal, draw unknowns in tension. I mean, you can look at it and say, well, it should be in compression, so I'm going to draw it in compression and just keep track of it. That's okay. Good practices if we're not sure of the direction of force, we just go ahead and draw it in tension. And if we pick up the negative sign, we know it's compression, just like we saw with method of joints. Now, let's do just kind of let's not put any numbers to it. Let's just look at maybe a generic example of something, some sort of a truss structure, kind of a fairly standard type of truss structure we might see. Might look something like this. Move up a little bit so we can see that a little better. Maybe a horizontal piece here, a horizontal piece here, angled piece there. Again, trusses are often composed of triangles because triangles are very stable shapes in order to build structures. They don't flatten easily like we see with something like rectangles or something like that. Okay, so if I have something like this, let's put pins at all the joints. We talked about treating each joint as a smooth pin last time. We'll continue with that. And so let's just label these A, B, C, D, E, and F. And we'll just apply some unknown forces here. P1 there, maybe a P2 there, so some kind of a weight and some kind of a wind load, we might say, if this were some sort of a truss bridge. Okay, so of course we know we could draw a free body diagram of the whole structure to find reactions as usual. AY, AX. I've got pins on both ends in this case, so I wouldn't actually be able to solve for the reactions right off. There would be 4 reactions here. There's 4 unknowns that, assuming I know the geometry of this thing, the dimensions, so I could find, even using a moment equation, I could only solve for 4 unknowns here, so I wouldn't be able to solve for all 3 of those. But what I can do a lot of times, if I have something that I can't determine the reactions right away, I can go ahead and write 3 equations that will relate these reactions in terms of each other, and then I can use, that gives me 4 additional equations I can continue on throughout the rest of the problem. And eventually I will probably have enough equations to find all the reactions, just not from this one, single free body diagram. You'll encounter those. I think I have assigned a few of those in the homework. You'll encounter some where you can't solve for the reactions right off, and that's okay. Just write the equations and then carry those forward. What else then? And let's say that the problem wanted to know the tension in just certain members, not the whole, or I'm sorry, I wanted to know the force in just certain members, not the whole thing, just in these certain members. What you can do is you can draw kind of an imaginary cut through your structure. It doesn't have to be a straight line. You could draw a circular cut if you really want. It gets a little cumbersome, but you could if you do it right. So if I draw a cut through this thing, and I draw a free body diagram, let's say, of this side, ABF, for example, and I've cut through members BC, BE, and FE with this imaginary saw blade that I've cut these open with. Again, here I've got 3 equations with 4 unknowns in the initial free body diagram of the whole structure. Now, if I've drawn this cut, what I can do, as I mentioned, I can draw a free body diagram of ABF now. So if I draw a free body diagram of ABF, I still have AY and AX. These haven't changed. I'm drawing the same side of this structure, so I'm going to draw them just how I've drawn them here. I'll draw them there. If you look at what we've cut through, I've cut through BC here. That is a horizontal force. BC, I'll draw it in tension. I've cut through BE here, so I'm going to replace that with the force that's carried through it, BE. And a horizontal FE. Or EF, I should say. Either way is fine. And I have the applied force P1. So these are all the things applied to the members that we haven't cut through on this side of the cut. AB, BF, AF. I've drawn those members here, and I've applied all forces that are applied at the endpoints of one of those members. And then I can write now 3 more equations. I have 3 more equations now, and I've added 3 more unknowns. I've added 3 more unknowns because up here I already had AX, AY, DX, and DY. I've already identified those as unknowns. Now I've identified 3 more unknowns. I've identified BC, BE, and FE. So I'm now at 6 equations with 7 unknowns. And yes, AX and AY are still unknown, but they're not new unknowns. Okay, well, we said we can cut a truss into multiple pieces and draw free body diagrams of the smaller pieces. So I've drawn a free body diagram of this piece, but I can also draw a free body diagram of that piece, of piece CDE. So if I do that, draw a free body diagram of CDE, which I'm not going to label that. But we are going to apply P2. I've got this D point there, and here I've drawn them like this. I'm drawing the same side of it. I'm not drawing opposing side. So I'm going to apply dy and dx as I've applied them here. If I solve for these and find a negative value and you want to apply it there instead of drawing it as unknown dx, draw it as whatever it might be. That's okay. Just be consistent about it. But now here's the thing. So these, I've drawn these in tension, and I don't know values for them yet. If I still don't know values for them, I'm going to continue to draw them in tension. BC, BE, and FE. And one might say, Steve, but you've drawn them different. They're different. Well, yes, they are. These are equal and opposite. Right? These are equal and opposite. Notice in this diagram, I didn't draw these forces. These BC, BE, FE. I've not drawn them here. They're there. They are there. The difference here is BE is both I guess BC. Both BC here and BC here, they're both right here, and they're equal and opposite. They're canceling out, so there's no need to draw them here. And the same thing with BE. I've got equal and opposite forces. So until I cut through, until I apply the cut, these forces are not exposed. They're internal and they cancel themselves out because they're equal and opposite. But once I cut into this, and this is something we're going to continue to do in Chapter 7. Chapter 7 is going to be all about taking objects, cutting through them, and then looking at the forces inside that you expose when you cut through them. So you can cut through anything on a free body diagram so long as then you draw the forces that are inside of that structure that you've now exposed. And we're going to continue to look at that. Like I said, we're going to continue looking at that at Chapter 7. I know it's a new concept, but let's look at this one. So now I can write 3 more equations. I can write 2 forces in a moment, or multiple moment equations, but I can write up to 3 more equations now. And there's no new unknowns here. Right? 0 new unknowns. Because I've already identified these 3 and these 2 up here and here. So now I have 9 equations I can write. And I only have 7 unknowns. So it's okay that I couldn't find my reactions initially. I can go ahead and write my 3 equations. I can probably find 1 or 2 of them, maybe up to 3 of them, but I won't be able to find all 4. But if I continue to draw free body diagrams, I continue to write more equations, I can get to a point where I have more equations than what I have unknowns. Hopefully that kind of helps. Why is this such a big deal? It's a loop. We just draw one free body diagram and we solve it. No, we're going to hit a point, and we've now hit the point in the semester where almost every time I'm going to have more unknowns than I've got equations multiple times. I'm going to have to keep coming back. Okay, what are you looking for now? Well, draw a free body diagram of what's going to have what you're looking for now. Now go ahead and see how many equations you have. Do you have as many equations as unknowns? No, what's still unknown? Draw another free body diagram where you have that, and then continue that process until you have as many equations as you have unknowns, and then go solve. This is method of sections. Right? So there's some pros and cons. Right? Well, we're going to actually put numbers to this and look at these, but let's talk a little bit about, before we kind of actually do an applied problem, we can take a minute or two here and just talk about some pros and cons. Okay. Method of joints, I'm just going to abbreviate these now. Right? I've got method of joints. That's what we did in the last lecture. That's where we you analyze a point, which means you can write 2 equations per free body diagram. This is a good method if you need to find force in each member. Method of joints allows you to systematically go through and analyze point by point and find every unknown, the force in every unknown member throughout the entire truss. I can go from one point to the next, continue writing equations until I find the force inside all of the members. That's method of joints. 2 equations per free body diagram because you're drawing equations of particles, except for, if you look at the free body diagram of the whole thing, then you can write 3 equations for this. But if you look at all the others, there's only 2 equations you can write in most method of joints free body diagrams because they're particles or points. Method of sections allows you to analyze pieces of the structure. it will allow you up to 3 equations per free body diagram. This is good. This method is good for finding force in specific members. Now, why in the world, Steve, why in the world would I need to find the force in each individual member? If I'm actually analyzing a truss for like a bridge or inside a house, I might need to know, okay, given this loading condition, given these forces applied to it, which one of these is actually going to break or burst. Meaning I should go through and look at each individual member and know, okay, this is the one, this one has the highest force, so it's going to be most likely to fail. This one has a lower force, so it's no problem. But if I have a software, or if I'm from experience, I can look at a situation and say, well, you know what? These specific members in this truss are under this condition are going to be the ones that are going to fail. So let's just analyze those and let's make sure that they're not overloaded. Because if they're not overloaded, the rest of the truss should be just fine. All right, that's a nice stopping place. I think we'll pick up with a specific example and put some numbers to this.